Hello, we're starting a new topic today, that of statistical quality control. Quality control of late has become an integral part of a manufacturer's portfolio. Quality control tries to avoid unnecessary wastages, basically aiming at maximizing resources and minimizing losses. This is an absolutely necessary controlling equipment on the part of a producer and manufacturer, and also it would add to be CV of a production controller. As consumer, we have all had the experience of purchasing a product only to discover that it is defective. It's defective in a manner that it doesn't function the same way as we would like to, and it is designed. This could be a new backpack with a broken zipper, or an out of the box malfunctioning computer printer. Many of us struggle to assemble a product the manufacturer has indicated would need only minor assembly, only to find that a piece of the product is missing or has become defective. This means the consumer has to take precautionary motive. As consumers, we all want and expect the product we purchase to function as intended originally. However, producers of products know that it's not always possible to inspect every product and every aspect of the production process all the times. The challenge is to design ways to maximize the ability to monitor the quality of products being manufactured and completely eliminate the defect, if any. One way to ensure a quality product is to build quality into the process. Consider Steinway and Company, the premier maker of pianos all over the world. Steinway has been making pianos since the last 130 odd years. It has started producing since 1880. Since that time, the company's manufacturing process has not changed significantly. It takes the company's 9 months to a year to produce a piano by fastening some 12,000 handcraft parts, carefully measuring and monitoring every part of the process. While many of Steinway's competitors, competing piano producing companies, have moved to mass production, where pianos can be assembled in a flat 20 days, Steinway has maintained a strategy of quality defined by skill and craftsmanship. Steinway's production process is focused on meticulous process design and extremely high degree of consistency. This has contributed to making it more synonymous with top quality. Statistical quality control is a term which is used to describe the sets of statistical tools used by quality professionals. Statistical quality control can be divided into three broad categories: descriptive statistics, statistical process control, and acceptance sampling. Descriptive statistics are used to describe quality characteristics. and relationships. Included in it is statistics such as mean, standard deviation, range, variance, etc. But statistical process control, on the other hand, involves inspecting a random sample of the output from a process and deciding whether the process is producing products with characteristics that fall within a predetermined range. SPC answers the question of whether the process is functioning as per the design or not. So statistical process control can be defined as a tool that involves inspecting a random sample of the output from a process and deciding whether the process is producing products with characteristics that fall within a predetermined range. So statistical process control is generally inspecting the random sample and deciding if that conforms to the quality control procedure established. Quality control, on the other hand, has something to do with quality. The third one, the acceptance sampling, is the process of randomly inspecting a sample of goods and deciding on that basis whether to accept the entire lot based on the results. Acceptance sampling determines whether a batch of goods should be accepted or rejected. The process of randomly inspecting a sample of goods and deciding whether to accept the entire lot based on the result. It can either be accepted entirely or rejected entirely. All three of these statistical quality control categories are helpful, real helpful, in measuring and evaluating quality of the products and services. However, statistical process control tools are used very frequently because they identify problems of quality during the stages of production. For that reason only, we devote most of the discussion to this category of tools. The quality control tools we will be learning do not only measure the value of a quality characteristics, they also help us identify change or variation that takes place. But first of all, we have to find out the measuring quality. Once we know the measuring quality, we will be able to identify specific tools which can be used for measuring the variation in the production and the units of production, in fact. Variation in the production process leads to quality defects and lack of consistency in the products. We'll take the example of Intel Corporation, the world's largest and most profitable manufacturer of microprocessors. Intel understands the quality defect and product consistency. Therefore, Intel has implemented a program it calls Copy Exactly. This Copy Exactly program has been installed in all of its manufacturing facilities. The idea that regardless of whether the chips are made in Arizona, New Mexico, Ireland, or any of other plants, they are made exactly the same manner. This means products are manufactured at any of these facilities using the same equipment, the same exact material, and same tasks being performed in the same order. The level of detail to which the Copy Exactly concept goes is meticulously planned. For example, a chip making machine was found to be a few feet longer at one facility than another. Intel made them match. When the quality of water at one plant facility was found to be different, Intel instituted a purification system to eliminate any kind of difference. Even when a worker was found polishing equipment in one direction, he was asked to do it in the approved circular pattern. But why such attention to exactness of every detail? The reason is to minimize all the variation that can be found, and as the variation goes on, the variability will increase and there will be product variances. That's why you will find that all the chips made by Intel conforms to the same standard. Zero variance products produced by Intel. If you look at bottles of a soft drink at a grocery store, you will notice that no two bottles are filled exactly to the same level. Some are filled slightly higher and some lower. Similarly, if you look at blueberry muffins in a bakery, you'll notice that some muffins are slightly larger and fatter, and some has more blueberries in it, some less blueberries. These types of differences are completely normal. No products, no two products in fact, are exactly alike. Because of slight differences in material, workers, machines, tools and other factors. These are called common or random causes of variation. Common causes of variation are based on random causes that we cannot identify. These types of variation are non-avoidable and due to slight differences in processing. Because it involves purely human nature of skill, it cannot be avoided under normal and natural conditions of production. The second type of variation that can be observed involves variation where the causes can be precisely identified and eliminated. These are called assignable causes. The first one was common causes. The assignable causes of variation are the second type. For example, you are using two different quality of raw material in producing products. An employee who needs more training or a machine in need of repair. In each of these examples, the problem can be identified and corrected. Also, if the problem is allowed to persist, it will continue to create problem in the quality of the product. If the same work is done in two different manners, then there is bound to be quality differences in them. So one of the causes is common causes of variation which cannot be avoided, but random causes that cannot be identified because of things involved which are not alike. But assignable causes of variation are causes that can be identified and eliminated. If they are not eliminated, then the products will be different. There will be more variation in two products of similar nature taken from the same set of samples. Descriptive statistics. Descriptive statistics can be helpful in describing certain characteristics of a product and also a process. The important descriptive statistics are measures of central tendency, such as mean, measure of variability, standard deviation, range, and measures of distribution of data like mode, and variance is coefficient of determination, etc. So descriptive statistics is all about quantitative data. The statistics which are used are known as mean, range, and standard deviation. basically we are going to discuss the statistical process control methods. Using statistical process control, we want to determine the amount of variation that is normal or common. Once you find the normal cause, then we monitor the production process to make sure production stays within this normal range. That is, we want to make sure the process is in a state of control. The most commonly used tool for monitoring the production process is a control chart. Different types of control charts are used to monitor different aspects of production process. In this section, we will learn how to develop and use control charts. A control chart is also called a process chart. It is a graph that shows whether the sample data falls within the common or normal range of variation. A control chart will always have a upper and lower control limits that separate common form of assignable causes of variation to that normal causes of variation. The common range of variation is defined by the use of control chart limits that remains within the upper and lower control limits. So the process is going to be out of control when a plot of data reveals that one or more samples fall outside the control limits. So assignable cause can happen when one of the data is beyond the control chart, beyond the upper and lower lines. The upper control limit is the maximum acceptable variation from the mean of the process that is required to be in a state of full control. Similarly, the lower control limit is the minimum acceptable variation from the mean for a process that is in a state of control. So we have a mean control limit, we have an upper control limit, we have a lower control limit. Things, batches of production, goods which are randomly taken should fall within the upper control limit and the lower control limit. You can see here in the diagram, the line on the upper segment is upper control line. Control line is exactly in the mid position. Lower control is in lower control limit in the lower part. The upper control limit and lower control limit actually describes if something falls within these higher and lower limits, then it happens because of normal and natural causes. But if something lies outside these upper and lower control limits, then the variation is out of control, and the variation is because of assignable causes. That you can find a fault with the system, with production centric system, with human error, everything. So any control amount, any point which is lying outside the upper control limit and outside the lower control limit is because of assignable causes. Anything that lies within these two lines, including the central line, is actually happening because of normal causes, natural causes, which are completely acceptable, but nothing should go out of hand. Particularly, something which is falling beyond the upper control limit is said to be out of control, and because of causes that can be controlled. What is a variable? Variable is a product characteristic that can be measured and has a continuum of value like height, weight, or volume. Attribute is a product characteristic that has a discrete value and can be counted. Control charts for variables monitor the characteristics that can be measured and has a particular continuous scale such as height, weight, volume, or width. When an item is inspected, the variable being monitored is measured and recorded in a particular manner. For example, if you are producing a certain kind of candle, the height might be an important variable. We could make samples of candles and measure their heights. the most commonly used control charts for variables monitor both the central tendency, which is mean, and variability of data, which is either standard deviation or range. It can be noted that each chart monitors a different type of information. When observed values go outside the control limits, the process is assumed not to be in control. Production is stopped and employees attempt to identify the cause of the problem and correct it. We are coming to the first type of chart, the mean bar chart. A mean control chart is often referred to as an X bar chart. It is used to monitor changes in the mean of a process. To construct a mean chart, we first need to construct the central line of the chart. To do this, we take a multiple sample and compute their means. Usually these samples are very small, with about 4 or 5 observations each. Each sample has its own mean. The central line of the chart is then computed as the mean of all sample means. X double bar is x1 plus x2 plus x3 plus the mean till the nth sample divided by k, the number of samples. To construct the upper control limit, we use the following formula. UCL is x double bar plus z into standard deviation of x bar. Lower control limit is x double bar minus z into standard deviation of mean, where x bar is the average of the sample means. Z is standard normal variable. Standard deviation of x bar is standard deviation of the distribution of sample means computed as standard deviation upon under root n. Standard deviation is population standard deviation, n is the sample size or total number of observations per sample. For example, a quality control inspector at Cocoa Phase Subdrink Company has taken 25 samples with 4 observations each of the volume of bottles filled. The data and the computed means are shown in the table. If the standard deviation of the bottling operation is 0.14 ounce, use this information, which is given in the next slide, to develop control limits of 3 standard deviation for the bottling operation. So the mean is given, the numbers are given. There are 25 samples of 4 samples each. So altogether there are 100 samples. What we do is we take the same set of data which is given to us. We will calculate the mean of each sample. There are 4 samples each. For example, sample number 1 contains 4 bottles, which is having the value of 15.85 ounce, 16.02 ounce, 15.83 ounce, 15.93 ounce. We add all the 4, divided that by 4. The average of these 4 bottles is coming to be 15.91 ounce. Similarly, for sample 2 and sample 3, we repeat the same procedure. We add all the 4 variables, divided by 4, we get sample of that, we get mean average of that sample. So we get the total sample variation, and the average total of the averages summation of x bar is 398.75. Just ignore the range which is calculated alongside because it is going to be used in the next example. Now we calculate x double bar, which is 398 divided by total number of sample, that is 25. So the double sample mean is coming to be 15.95, which means 15.95 is the sample mean of the entire set of population sample, that is 100 samples. The upper control limit is x double bar plus z into standard deviation of x bar. 15.95, we are given that the z is 3, so 3 into 0.14 divided by under root 4. Standard deviation of x bar is calculated as standard deviation divided by under root n. So the upper control limit is coming to be 16.16. The lower control limit is coming to be x double bar minus j into standard deviation of x bar. That is, we're changing the sign. So lower control limit is coming to be 15.74. The control limit is 15.95. Upper control is 16.16 and low control limit is 15.74. We have charted this into the graph. 15.95 is the central control limit, which is given as the very thick black bar. Upper control limit is given at the above the dotted line, and lower control limit is given below the control line as a dotted line. So you can see, after dotting all the points, all the means that we have calculated, means we are taking from the previous table 15.91, 15.99. The maximum of the mean is 16, 16.02 and 16.05, 16.03. So under the circumstances, no mean is lying above the upper control limit. So all the means that we have calculated are actually scattered along with the control line, little bit above and little bit lower. But no point, no mean is charted either above PCL or below LCL. This means to say that all the samples are lying within the control limit chart. So the mean control bar says that the process, the samples which are taken from the process are actually fully controlled, and there is no question of any deviation happening out of control. So these activities are lying exactly within the common cause of error, and there is no assignable cause because it is within the control of the process. Now we are coming back to the second type of charts, range chart. The range chart is another type of chart, control chart for variables. Whereas X-bar charts measure the shift in central tendency, range chart actually monitors the dispersion or variability of the process. The method for developing and using R charts is the same as for X-bar charts. The central line of the control chart is the average range. The upper and lower control limits are computed. The control limit is R bar. Upper control limit is D4 plus R bar. And lower control limit is D3 minus R bar. The values of D3 and D4 can be obtained from the table which is given under the heading of table 6.1. The table is given for range chart that you can see for the sample size. We can calculate D3 and D4. You can see that for a sample size of 2 to 7, D3 doesn't have a value. D4 has positive values, higher values for low samples, and as the sample numbers goes up, the value is actually coming down. But D3, the values are smaller in the beginning, but as the sample size is going up, the D3 value is going up. We are taking the same set of example that we have taken earlier. The quality control inspector at Cocoa Fizz would like to develop a range chart in order to monitor the value dispersion in the bottling process. We are using the same data set that we have taken for the last question. The samples are given to us. There are 25 number of samples, each containing 4 bottles. The bottle volume in ounce is given. Now we have to calculate the range. For sample number 1, there are 4 bottles, the highest being 16.02 and the lowest being 15.83. So by subtracting the lowest from highest, we get a range of 0.19. For the second sample, the highest value is 16.12 and the lowest value is 15.85. So by subtracting 15.85 from 16.12, we get a range of 0.27. We calculate the range for all the samples. By adding the range, we get a maximum range of 7.17. Summation of the range is 7.17. From 7.17 we will calculate R bar. R bar is summation of range divided by 25 the sample size, which is 0.29. So average range is 0.29. Number of bottles in a sample is 4. From the table, for a sample size of 4, the value of D4 is 2.28 and value of D3 is 0. Exact values has been taken for computational purpose. Value of D4 for a sample size of 4 in a sample is 2.28 and D3 is 0. So the resultant control chart LCL is D3 multiplied by R bar, which is 0 into 0.09 is 0, and upper control limit 2.28 into 0.29, that is 0.6612. So we have lower control limit, which is 0, not existence, and upper control limit is 0.66, and control limit is 0.29. We have to put that into the bar. You can see again the lower control limit is the x-axis itself because the value is reduced to 0. The upper control limit is 7.29. So, pardon, the upper control limit is 0.66, which is taken between 0.6 and 0.7 on the y-axis. The control limit or range of mean of range is 0.29, which is taken as a very thick black line in the middle. All the ranges has been plotted. All the range. The value of the first range is 0.19, which is a black tick mark along 0.20 corresponding to 1 on x-axis. The second value is 27, which is corresponding to the second sample. We can see here that none of the values are actually lying less than that of LCL or more than that of UCL, which goes on to say that out of the 100 boxes which has been taken in 25 samples, nothing has been out of control. So the entire process is within the control. So quality control system for verifying and maintaining a desired level of quality in a product or process by very careful planning and use of proper equipment, continued inspection and corrective action as required. Objective of quality control is to develop a scheme of sampling a process, making a quality measurement which can be worked upon to minimize the wastages. So once the samples are taken, measured, then a decision can be taken whether the sample is actually conforming to the process, whether it is in a stable state or in control or out of control. If it is found to be in control, then there is nothing to be worried about. But if it is out of control, then we must look at the quality of the material, the quality of equipment, quality of labor, skill, everything. So we have come to the conclusion of quality control, statistical quality control part 1. We'll be discussing more quality control measures in the next session. Till then, thank you very much.